Alright, this is the final video of Chapter 9. I'm on Section 9K, and it's pages 29 to 32 in your Chapter 9 notes. So the final section is about independent events. And here's our first definition. A and B are considered independent if the occurrence of each one of them does not affect the probability that the other occurs. So if we go back to that conditional probability we just learned in the previous section, the probability of A given that B happens will equal the probability of A given that B doesn't happen, and that will equal the probability of A. So in other words, the probability that A happens given that B happens or doesn't happen still equals the probability of A. So B happening or B not happening had no impact on the probability of A occurring. So now once we do that, we can simplify a multiplication rule. And again, I feel like we've already seen this in the chapter. We're just formalizing it now, that if you just learned a conditional probability multiplication rule, the probability that A and B both occur is the conditional probability of A given B multiplied by PB. Well, because this event B happening no longer matters, then I can rewrite that as P of A multiplied by P of B, and this is the multiplication rule for independent events. So if you know two events are independent and you're asked to find the probability that both A and B occur, you're just going to multiply two probabilities together. On the other hand, if you're asked to verify that two probabilities are independent, two events are independent, you have three options available. You could demonstrate that the probability of A intersection B separately from A times B give you the same answer, or separately demonstrate that A given B equals the same thing as A, or that B given A equals the same thing as B. Okay, so a couple of concepts here. First, this multiplication rule. Second, this thing about verifying two events are independent. And then finally, last important thing in the chapter is often when we look at a sequence of events, we want to know the likelihood that at least one of two or more independent events happen. So for that, you're going to see the complement rule used twice. So the complement, if you think about logically, at least one happening, the complement of it is none happen. So the first line here should make sense to you, that the probability of at least one happening is 1 minus the P probability that none happen. Well, the word none happening could be retranslated into all of the events don't happen. So if P is the probability it happens and 1 minus P is it doesn't happen, then all I have to do is take those independent probabilities, multiply them together, and then that 1 minus came from the original use of a complement. Last important note is, now that you're hearing this word independent and you've previously heard the word mutually exclusive, I want to make sure that you see the difference between mutually exclusive and the word independent. So mutually exclusive simply means two events can't simultaneously happen. So when things are mutually exclusive, I'd be telling you that A intersection B's probability is 0. If two events are independent, I'm telling you that A intersection B's probability is found by multiplying PA times PB. Okay, so those are the concepts in the section, and here's the model problems. So in our model problems, many of these have the flavor of giving you a list of probabilities and asking you to find some other probability. So in that case, you saw previously that formulas do tend to come in handy, because I'm not really summarizing a word problem into a Venn or a tree. I'm just using this given list of probabilities. So in this case, in part A, 1, if I have to find the probability of A intersection B, and I see that list given, one of which is the union of A and B, I'm going to go back to what I learned in a previous section, that the addition rule formula will come in handy here. So the A union B probability is 1/2. The probability of A is 2/5. The probability of B is 1/3. And then we can find that missing A intersection B probability. So to find that missing A intersection B probability, just do some math on your calculator, and you can end up with 7/30 for the probability of A intersection B. All right, A part 2, the probability of B given A. Well, you've seen that as a formula before. In conditional probability, if you're using a formula, you put the intersection probability in the numerator and the given event probability in the denominator. So the B intersection A probability, we would have just found in the previous part as 7/30. A's probability is 2 out of 5. Again, assuming you could reduce this by hand or with your calculator, you can turn this into 35/60 in fraction form. All right, A part 3, probability of A given B. Okay, you're going to see we're not going to get the same answer because formula-wise, I'll take the intersection of the two, divide by the given one. So the A intersection B probability is 7/30. B's probability is 1/3. And if I simplify that result, I'll get to 21/30. Okay, and then finally our events A and B independent. So if I'm going to do part B, I'll have to squeeze it in up here because I'm out of room. Here's where I'm going to check that if I look what I just found the probability of A given B, and that answer was 21/30. And then I have to separately figure out the probability of just A. Well, that was 2/5. Clearly, 21/30 is not the same as 2/5. So I'm going to write therefore, I'll put that 3 dots in for therefore not independent. Okay, next page. Now I have a stem of a question with 2 given probabilities along with the important information that the 2 events here are independent. So I have to remember how I can use that. So when I go to answer the probability that both X and Y occur, both is an AND problem. If you tell me 2 things are independent, I'll find an intersection probability just by multiplication. So all I have to do is multiply 0.5 times 0.7 to get 0.35. Part B, if you ask me for X or Y, that's the union or the addition rule. So I expand that to PX plus PY minus PX intersect Y. Plug in all that stuff, 0.5 plus 0.7 minus 0.35 to get 0.85. Part C, neither X nor Y. That means X doesn't happen and Y doesn't happen. When they're independent, I just get to multiply these 2 probabilities together. So X prime's probability is 0.5, Y prime's probability is 0.3, multiply to get 0.15. Part D, X but not Y, X happens and Y doesn't. Multiplication rule again, PX times PY prime, so that's 0.5 times 0.7 or 0.35. Oops, sorry, 0.5 times 0.3. Or 0.15 again. And part E, the probability of X given Y, formula tells us to take X intersection Y in the numerator over PY in the denominator. X intersection Y we found up there in part A was 0.35. PY was given to be 0.7. So we'll just get 0.5 for this. All right, so you can see that the problems in this section should feel like we're just kind of following rules and formulas. Question 6, another list of given probabilities, and also the important information that the events being described are independent. So if we're describing events as independent, we have to know how we're going to use that. Okay, so if I have A intersecting B is 0.1, A intersecting B prime is 0.4, for me, in order to work through this, tools from previous sections, I'm going to put this in a Venn to help map out the regions if this is set A and this is set B. So the first region I can fill in is 0.1. A happens and B doesn't is 0.4. Okay. The probability of A union B prime is what we're asked for. So let's think about this. Using the addition rule, I'm going to need PA. I'm going to need B prime. And then I'm going to have to minus off A intersection B prime. All right, so the first thing we're going to do is we're going to notice from the Venn that the A intersection B probability is 0.1 and that P of A is 0.5. But A and B are independent, so that means I can write myself an equation that 0.1 equals 0.5 times PB, P of A times P of B. So that means 1/5 is probability of B. So now that I know that that's 0.2, I get to put 0.1 in this region and 0.4 out here. So that's going to help me go back and solve the original problem. P of A is 0.5. P of B primed would be 0.8. And A and not B would be 0.4. So solving this, we get 0.9. Okay, that's not an easy problem. It does take a lot of focus on some algebraic thinking, some Venn diagram to help demonstrate the probabilities, and then the rules for independence as well as the addition rule. Okay, final page of chapter 9. All right, we have A, B, and C trying to solve a problem, and they've got these probabilities of being able to solve it. What's the probability that at least one can solve the problem? So we have this probability of at least one question. So let's follow the at least one model. Probability of at least one solves puzzle is 1 minus the probability that none solve the puzzle. So none solve the puzzle means all 3 people can't solve it. So that's 1 minus. Person A can't solve the puzzle. That's 2/5. Person B can't solve the puzzle. That's 1/3. Person C can't solve the puzzle, 1/2. So it's 1 minus 2 out of 30, 28 out of 30 chance. Okay, so the idea of at least one as 1 minus P none is a rule worth remembering, because solving that with a tree diagram or a sample space from rules earlier in the chapter would not be efficient. Okay, finally, a jar of tickets in a lottery. I like to draw the jar. I have 4 of them. So that means in this jar there would be 4 winning tickets. And if it's 500 tickets, that means 496 losing tickets are in there. And we're going to pick without replacement. So if I pick without replacement, part A is saying, what's the chance that I get the first 3 prizes? Well, that means a win-win-win would have to happen. So the first winning probability would be a 4 in 500. These are AND problems. AND means multiply. And the second one's a winner. Well, this is done without replacement. So there's now only 3 out of 499 because the winning ticket was set aside. And now 2 winning tickets have been set aside, so there's only 2 winners left. So if you multiply that together, that's going to be pretty small. If you multiply out the numerators, it's 24. If you multiply out those denominators, it's 124 1,251,000. So a really small chance of winning all three prizes. Part B, at least one. So the idea of at least one wins is 1 minus the probability none win. So it's 1 minus the probability all three losing tickets. 1 minus, okay, losing ticket, 496 out of 500. Multiplied by 495 out of 499. Multiplied by 494 out of 498. Okay, so your calculator can handle this. All right, it's still a really small chance that I have at least one winner. This would be the number on my calculator screen. And of course you could put 3 sig pig answer down too. Yay, that's it. That's the end of chapter 9. Hope these videos helped. This should be enough information for the final worksheet, number 4, final assignment of the second semester, due Tuesday, May 5th. That's it. See you next class.